So we're going to pick up from the atomic timeline as your kind of background information. So you might want to go look back at the project you guys did in September. At about the period of time when Rutherford and the Curies were working, so the beginning of the 1900s, at this point in time in science, we thought we understood it all. We thought that essentially, now that we know about protons and neutrons and have a periodic table, and in other things in physics, we had Newtonian physics, which explains like how things fall and how when you throw something, it's always going to make an arch, like that. We thought with those sort of theories and ideas in science that was the end of the story. We thought we knew everything. And as you progress in education, you're going to learn this for yourself, I hope. The more you know, the more you realize that there is an infinite number of things you don't know. And so this was what was happening to science in the 1900s. We were realizing there's so much more that we really don't understand than we even knew about at that point. So, at the turn of the century, the 1900s, we only had 4 mysteries left to solve. And those 4 mysteries could not be explained with Newtonian physics, okay, with the physics that was invented by Newton, with calculus and all of that stuff. So I'm not going to go into a lot of depth about these 4 mysteries, but they are really, really interesting. I would recommend studying it on your own. It's not really part of the course requirements, though, but here they are sort of summarized really, really quickly in 1838. So, like, a long time ago, right? Michael Faraday invented cathode ray tubes, and actually those were the equipment that J.J. Thomson used, right? So Faraday wasn't part of your atomic project, your timeline project, but J.J. Thomson was, because he discovered electrons using cathode ray tubes. But anyway, the interesting thing about cathode ray tubes is that you can't see the light source. All you can perceive is if you have a special material, kind of like a glow-in-the-dark paper inside of the cathode ray tube, then you can see the light reflecting off of that. But normally it is a source of light that we don't perceive, so it's not in the visible range. But if you put an object inside, whether it's paper that fluoresces or not, if you put an object inside of that cathode ray tube, they will cast a shadow, which is weird. Can you imagine seeing a light bulb with no apparent light source, but there's a mysterious shadow from objects in the beam that you can't see? That's crazy. It's just bananas. There's no other way to explain it. It's crazy. That was known since 1838, but nobody had an explanation for it. So that was one of our mysteries that remained in the beginning of the 1900s. Another one is called blackbody radiation, which was discovered by Kirchhoff. And Kirchhoff is his science is actually really interesting too. Basically, blackbody radiation is what happens when you have like your stove, okay? And so if you have a stove with the little ceramic thing, you know what? Let me just show you. Hang on. Okay. Here we are in my kitchen, and the only source of light right now is my computer screen and a window around the corner. So that's it. And so what I've done is I turned my stove on. In real life, that doesn't look purple. I don't know if it looks purple to you guys. On my recording, it kind of does. In real life, that's red. That's my stove. And so what we have here is a kind of ceramic composite in a coil, and we are running electrical energy into that. And when it gets hot, because the energy has nowhere to go besides just making molecules vibrate faster, it produces some light. And so you can kind of tell if I cool this down, and I can feel that heat from a long way away, right? That's some infrared radiation that I am perceiving. And as we watch, let's cooling down little by little, and you can start to see that the red gets more orange. And eventually we're going to see it go back to the original color, which is black. This is black body radiation. Okay? When hot objects emit light, that's black body radiation. We're going to go back on a field trip to my office and resume the conversation there. Okay, so now we're back. So that was an example of black body radiation, and that actually exists all over the universe. Anytime something is being heated, it emits light. Stars are a great example of this. If you look up at the sky at night, you'll actually see that the stars have different colors. Those colors are based solely on the fact that it's burning at different temperatures. Each star burns at various different temperatures. And so if I could somehow make my stove continue to heat even hotter, we would go through the entire color spectrum. So let's go back to the first slide and we can see what the color spectrum was. So here you see I was in kind of the red region. It'll get brighter orange as it gets hotter, and then yellow. It does turn green, but it's very brief actually. And then you get blue. This is the region of our burners in the lab, right? They produce two different colors of blue flame. One's kind of lighter and the other one is darker. The darker is the hotter one. Okay, so we've seen that. And if you could keep going past the temperature of a Bunsen burner, it would turn violet and then ultraviolet, and then X-rays begin getting emitted, and then gamma rays. And so it goes up like that as things get hotter. It doesn't matter if I turn my kitchen light on or if I shine a purple light on the kitchen burner. It's gonna be the same color. And so this is a really strange phenomenon when you think you understand how light works. To have something that has color of light only depend on the temperature, not on what source of light is shining on it. That's a really puzzling situation to be in, right? In the blackness of space, we see stars because of black body radiation, because they produce so much heat that they have to glow. And then in 1877, Boltzmann hypothesized that energy must be discrete, meaning individual small particles, the same way that we think about atoms. Now, energy isn't atoms, right? Atoms take up space and have mass, and energy does not take up space and it does not have mass. But from a mathematical perspective, energy should have a discrete amount in the way that matter has discrete particles. Okay, that was the basis for Bohr's idea, Niels Bohr, who was part of your atomic timeline project. That's the basis for Bohr's idea of orbitals, which is the basis for Schrodinger's idea of orbitals. But each person had a slightly different take, and it turns out Schrodinger solved the problems with his math. Finally, we have the last mystery in 1905. Now, this was after the discovery of the periodic table. It was after the discovery of electrons, right before the discovery of protons, right? There's this phenomenon called the photoelectric effect, and there's a great FET simulation, F-H-E-T, yeah, like that. If you want to explore this, basically, if you shine the right color of light onto metals, and it depends on which metal it is to get the right color, electrons get ejected from the surface of the metal. Now, this is not something you can see with your eyes. Okay, we can't see electrons. We could measure voltage, though. You could measure charge if you had the right setup. But only certain colors of light would cause electrons to eject off of any given metal. And each metal needs different colors. And it was impossible for them at the time to figure out why. Okay? So Max Planck did a lot of things, one of which involves Planck's constant that is used in chapter 6. It's the value h, lowercase h. But that was all started because he was exploring the photoelectric effect. And as a result of that work and really good scientific method, he discovered a bunch of other things along the way. All right, so the brightness of the light doesn't matter. All that matters is the frequency and wavelength. So these slides have some interesting details about these four phenomenon. This is the PhET simulation I was talking about. It is worth your time to go explore and see if you can answer these questions. But it's the understanding that he got from studying the photoelectric effect gave us the idea that light should behave like a particle. And so that's where Planck's equation comes from. Energy equals Planck's constant times frequency. That's nu frequency, not v for velocity. Okay, so frequency. And so that's where Planck's constant comes from, and it turns out it is now the basis for what a kilogram is, which is another phenomenal story that we don't have time for yet. And our last source of mysterious behavior was actually used quite a lot. Marie Curie proved she found 2 new elements, and many other scientists as well, by using this phenomenon, but nobody understood why it works. Essentially, if you invent something called a diffraction grating, which is now just a piece of plastic with ridges in it at very even intervals, kind of on a microscopic scale, what will happen when you look through the diffraction grating is a light source, like a lamp, there, a light source will be split into its component colors. So instead of seeing the white light in our light bulbs, if you use a diffraction grating to look at a light bulb, you're going to see individual colors of lines. And those individual colors add up together to see the total color that we get from our light bulbs. So these diffraction gratings are interesting, and it turns out if you take an element and you burn it in a flame or a cathode ray lamp, and you look through a diffraction grating at that burning element, each element has a certain fingerprint. That fingerprint is known as the line spectra for that element. So in this case, in lab, when we're doing the spectrophotometry lab, where you are figuring out the concentration of Gatorade, that little instrument is based on this idea. All right, so you have a light source. In our situation for lab, it's a little cathode, a little LED in there. And then you have a small opening for that light beam to go through. And then you hit a diffraction grating, the plastic with ridges, or a prism. They both do the same thing. And it will separate the light out into all the colors. So if we started with white light, full spectrum light, we would see all the rainbow colors. The sun does this. The sun is a full spectrum light. If you started with a cathode bulb that is burning hydrogen gas, hydrogen looks pink to us with our eyes like this, but when you look through the diffraction grating, you'll see that that color is actually due to very specific bands of color. So we have kind of a dark purple, a lighter purple, indigo. Some physicists would yell at me for calling this indigo. There's some argument over what the name of this color is, but I don't have a better name, so I'm going to call it indigo. And also a red, all right? And so this is the line spectrum of hydrogen in the visible range. There are more lines, but these are the ones we can see. When we do this in class, sometimes I've found people either see really well on the purple side of things, or they see really well on the red side of things, and they have no idea that this is true for their eyes. I personally see in purple quite well. The red, when I look at this for real, is pretty hard for me to perceive. This has been photoshopped, so the intensity of all 4 colors is equal, and hopefully everybody can see them. But in real life, that's not the case. In real life, some people have better vision on the red side, and other people have better vision on the purple side, and it's just a matter of your biochemistry. Neon, we've seen these neon signs, the open signs, those are called neon signs, but only the ones that are orange are actually made out of neon. But neon is a complex line spectrum, but it's very distinct. So we can tell what other stars have in them, what elements are burning in them, what elements are being created in them by using these diffraction gratings and telescopes, okay? And you get a pattern of lines that indicates what elements are there. For our sun, we're mostly burning hydrogen and creating helium. So we're going to get mostly the lines due to hydrogen and a few of the helium spectrum thrown in for for flavor. Okay, so these are the four mysteries that were not solved at the beginning of the 1900s, and we thought that regular, plain, classical physics, which is called also Newtonian physics, was going to solve these mysteries. If only we could just figure out the one equation that was missing. As you might expect, this was not that simple, and the ramifications of these four mysteries and their answers is still affecting our world today. A lot of the technology that we use every single day depends on the exploration of quantum mechanics, and quantum mechanics was born from trying to understand these four mysteries.